So now I would like to continue with powder handling. So how to work with powders, or this may be related to the system inside the AM machines. Okay, the powder delivery system for powder bed fusion. Basically, this should have a reservoir of sufficient volume. Why? Because you should not stop the process of additive manufacturing for refilling the powders during the process, for sure. So you should provide enough materials inside the reservoir, and therefore the reservoir should have sufficient volume to store the materials to provide to the additive manufacturing process without uh, interruption. Sufficient powders, for sure. The system should spread the powder to form a smooth and thin layer. Because you please remember that for certain materials, for example, stainless steel 316L, the minimum thickness of layer can be 20 microns. So it's relatively thin layer, and therefore you need a precise powder delivery system in order to spread the powders to form a smooth and thin layers. And the system should guarantee that there's no excessive shear forces when spreading powder. Yes. In other words, there's no disturbance on the previous layers. Regarding the powder fitting characteristic, yeah. So the powder system must ensure the flowability of powders. Yes. This can be done by reducing the particle size to, how can I say, basically you should reduce the size of the powders. Yeah. But if you reduce the size too much, you reduce too much the size of the powders. So I would like to find an example, because if the size of the powder is too small, then they tend to stick to each other. So in this case, it's easier to have the agglomeration. So again, finding a trade-off, or the balance, is also important to guarantee the full abilities of the powders. Yes. This means that if you reduce the size too much, and then you may have the increasement of the friction and electrostatic force. And in that case, you lose the flowabilities, and therefore this should be careful performed. The surface area per volume ratio of the particles, yeah, if it increase and the surface energy is increased, yeah, and more reactive. Yeah, for sure. Especially for example, magnesium or aluminum powders. So if you reduce the size of the powders, which means that the surface of these powder within a specific volume will significantly enhance, and therefore the probabilities uh, that the oxidation reaction occur can be increased. Can be increased. Yeah. And you should pay more attention, especially in the case of aluminum powders. So because it's easy to react with oxygen, or easy to be burned with electric discharge, and therefore concerning the handling of aluminum powders. So the powder should be kept inside the inert atmosphere to prevent some kind of oxidation reactions, or if it's react with the moisture, and it can be the exothermal reactions, and the heat, yes, will have negative effect to those who handle uh, powdered metals, like in the case of aluminum powders. And when handled, the small particles, yeah, can float as a cloud. Mhm. And the thing is that the particle, when it float as a cloud, they can stick on the surface. Yes. For example, the surface of the sensor. Yeah. It has a negative effect concerning deflection of laser beam, which reduce the effect of heating the layer of the materials, and therefore, uh, you know, negatively influence the welding process occur with the additive manufacturing, and therefore you should pay attention to this. Damaging the moving part, yeah, but it's just some information to let you know about the fact that yes, if you reduce the size of the particles, yeah, what happened? And what you need to consider with the powder feeding system. And as a result, the powder delivery system should minimize the airborne particles or those small particle flows at the cloud. Yeah. That's because when this is the deflect, yeah, the laser beam, and the laser beam cannot irradiate onto the area that is provide heat in order to locally melt the powders. So in that case, you have the lack of fusion defect, and therefore the porosity of the part after the sintering process will be increased, and that should be avoided for sure. And last but not least is the issue of safety when handling powders. So for sure, because if you breathe the powder, and the powder can go into your lungs and stick there for a long time, and it's quite detrimental to human health. And concerning the powder's production process, so I have mentioned it in the previous several slides. We can use the gas atomization process or water atomization process. But for the typical gas atomization process, firstly we have uh, the input metal alloys. Yeah. And then we use the induction melt or furnace melt in order to create the molten pool. So the molten material. So the initial material need to be melted, yeah, inside an oven, and then the atomized process with stream of gas, like for example the inert gas, like argons, will be used in order to support the process of atomization. And below you can collect the powders, and then you use the sieving process in order to eliminate some kind of large particles or the agglomerations. So just and distinguish different size range of the powders. This process of gas atomization can be used to produce high purity and spherical powders. But comparing to the case of water atomization, the process is more expensive and may have uh, the gas porosity because the gas can be entrapped inside the powders, and therefore you have the porosity inside the powders. Yeah. And if the powder has porosity, and therefore if you use the additive manufacturing process to fabricate the part, and then the pore is thin inside the powders, and when the powder is joined with another powder by wetting process but not completely melt, and in that case the porosity is thin inside the additive manufactured part, and you should pay attention to this issue. Those impurities like iron, yeah, can be picked up during powder creation, and if we consider the case of titanium material, and then for sure iron can be considered as undesirable factor. The plasma atomization can produce uniform and spherical powders. Yeah. But since the feedstock material for plasma atomization require wire form of the materials, and therefore you need additional processing step, you enhance the cost. Yeah, for sure. Titanium powders uh, are an example. This can be produced by this process, and can we can achieve the size range of output material of 106 microns. For the moment, the limitations associated with the gas atomization process are the cost, the cleanness, whether or not we have the uniform powders, because we may have the irregular powders, irregular form powders. And uniform powder is quite important because it affects the flow characteristics. Yes, the flow abilities. Yeah, and is addressed in uniform powders for sure. So let's think of the fact that if you have inside the nozzle the agglomeration, and it can block the nozzle, so the process cannot be continued anymore. Wire and electrode. Yeah. So metal wire can be in many forms, and still under the development for AM. Yeah. For the wet wire. Yeah. So for the moment, we have the close control of chemistry, impurities, and dimensions. Because we also, how can I say, develop the wet wire for the traditional wedding process. So not only for like wedding, alloy filler wire for commercial arts wedding is for a wide range of applications. So we know pretty well about this. I'm sure you know that. Basically, the wedding area is even better than the material that's subject to the joining process. Both the metal wire and electrodes are now in use by the metal additive manufacturing system, and everything has two side effects. So wire and electrodes has both advantages and disadvantages. Advantages are, for example, wide range of alloy available. So it means that it's cheaper to buy if they are available. Existing based on the application. Disadvantages, yeah, is concerning probably the accuracies of the additive manufacturing process, because we have large modern pool to melt wire. So it affect negatively the deposition accuracies of the additive manufacturing process. And in order to, how can I say, melt a large wire comparing to small powders, you need a higher heat input. Higher heat input inside the building chamber is mean that uh, you may have the possibility of thermal gradient when additively fabricate the part. In other words, you may have the stress concentration, the residual stress caused by thermal factor, and if it's released, and you may have uh, the distortions, or using the wire filler, you may have the possibility of part distortion after the additive manufacturing process. So on the right side, you see the wire spool. Yeah, and the wire is made of 316L stainless steel. And below, yeah, you can see that how the wire is fed to the additive manufacturer system using electron beam as heat source in order to build up the part layer by layer. Almost the last line of the chapter 2, we uh, we can talk about we can talk about other types of materials. For example, composite, intermetallic, and metallic glass. For example, metal-matrix composite. So this means that we can use the main material is the metals, but then this can be reinforced with non-metallic compounds, and therefore the result materials will have the combination of properties of different constituents. So, for example, if we use the tungsten carbide, yeah, embedded in a ductile metal matrix for cutting tools. So the properties of the cutting tool will have the property of tungsten carbide and the properties of metal matrix for sure. That's why we have the combination of properties. And the metal fillet composite, the aim of using this kind of composite for lowering the material cost and improve the ease of fabrication. Like in the case of polymer rig coated with tungsten powders. Intermetallic materials is the combinations of different metals to form the large complex crystal structures. Yes, this this is uh, this is a complex material. For example, titanium aluminide. So it can be introduced in the chapter 3 of aerospace materials, titanium aluminide. But we will not focus so much on these materials. But it's among the type of titanium alloys. As the strengthening phases found in aerospace superalloys for fabrication of aerospace engine components. So the properties of titanium alloy is low densities, mean that it's light materials, light. Uh, yeah. uh, High oxidation resistance is mean that affinity with oxygen is low, so it's hard to react with oxygen. High strength and higher sweet temperatures. But comparing to the case of the can base superalloys, the titanium alloys can withstand uh, lower maximum temperatures comparing to the case of nickel based superalloys. Amorphous materials. So the term amorphous, yeah, vô định hình, amorphous. Amorphous material and metallic glass. Also uh, so basically you can understand the material as a matter with disordered atomic structures. So if you have the crystallized structures, then each atom will occupy a certain position within a lattice structures of a matter. So everything is in order. Everything is in order in a specific positions. Even if we provide heat and the atom at a specific position can uh, associate. Uh, I'm sorry, not associate. Can oscillate or fluctuate around the equilibrium position, but then it's still uh, in a fixed position, let's say. But for amorphous materials, so atoms has the do not have an ordered position with atomic structures. And this can be formed by performing rapid cooling from the molten state. The aim is to avoid the crystallizations. Cái vật liệu vô định hình hay còn gọi là vật rắn vô định hình thì chúng ta biết rằng là đối với cái vật rắn tinh thể của chúng ta, ví dụ như là kim loại chẳng hạn, thì các cái nguyên tử nó ở những cái vị trí xác định trong cấu trúc của mạng tinh thể. Nếu như chúng ta có gia nhiệt thì các cái nguyên tử nó nhận được cái năng lượng tự do, nó sẽ dao động xung quanh cái vị trí cân bằng thôi. Tuy nhiên thì sau đó nó cũng vẫn phải trở về vị trí cân bằng, là ở những cái vị trí xác định trong cái cấu trúc mạng tinh thể. Thế còn đối với những cái vật hoặc là những cái vật liệu vô định hình hoặc là dạng metallic glass này chẳng hạn, thì người ta tự tạo thành bởi cái gì ạ? Bởi cái việc là sau khi mà đã nung lên trạng thái lỏng thì chúng ta làm nguội rất là nhanh để loại bỏ cái quá trình kết tinh, thì nó không tạo thành dạng tinh thể. Có nghĩa là các cái vật liệu chúng ta nó sẽ không, các cái nguyên tử nó sẽ không ở cái trạng không ở vị trí có trật tự ở trong cấu trúc. Thì đấy là cái and the last line of the chapter highlight the content regarding the recycle and reuse of metal powders, especially for the additive manufacturing process. Yeah. Just to protect the environment, and because of the economic factors, because we can reuse, we can recycle, and we save the money. Yes, comparing to the case of we have to start the whole process in order to fabricate completely new materials. The impurities, contamination of additive manufacturing materials can occur inside the building chambers. Yes, because you know that we have the shedding gas in order to act as like a shell to prevent the materials from reacting with those gas like oxygen, nitrogen, and so on. However, the gas can contain the impurities, yeah, or even the delivery gas. So when we transfer the powder, yeah, we may use the flow of gas, which can be used to carrying out the powders to the certain position, and this gas may contain impurities, lead to the impurity contamination of AM materials. So we need to store the powders in appropriate way, yeah, proper handling, in order to prevent this impurity. Or in other words, improper handling the powders can create the impurities. And therefore, we need to evolve the process of handling. Or if we have the impurities, or if we want to save the environment, and then we need to recycle and reuse the materials. Thực ra thì cái vấn đề recycle thì chúng ta biết rằng là để bảo vệ môi trường và cái vấn đề về mặt kinh tế thôi. Thế còn cái impurity, cái sự nhiễm bẩn, nói nôm na như thế, xuất hiện những cái tạp chất chẳng hạn ở trong cái vật liệu AM thì nó có nhiều nguyên nhân lắm, chứ không phải là chỉ có từng này cái nguyên nhân mà tôi kể ở đâu, đúng không ạ? Nó có thể là do cái môi trường ở trong cái building chamber, và trong khi vận chuyển giả lỏng ấy, một trong các hình thức vận chuyển đối với powders là vận chuyển giả lỏng, có nghĩa là đưa các cái luồng không khí vào, và những cái luồng không khí đấy dùng để vận chuyển các cái hạt powders, nó di chuyển từ vị trí này đến vị trí khác, thì người ta gọi là delivery gas. Thì một trong những cái môi trường ở building chamber, cái delivery gas mà nó contain impurities, nó có thể làm cho contaminate cái AM material của chúng ta, đúng không? Cái storage of powder nó cũng có thể cái môi trường mà cất giữ, đúng không ạ, nó cũng có thể nó có hơi ẩm này, nó có chứa oxygen này, thì nó cũng, hoặc là improper handling thì đều có thể gây ra impurity, và chúng ta cần phải cải tiến các cái process đó. Và chúng ta đương nhiên là những cái mà đã chứa có impurity thì rõ ràng là chúng ta phải recycle, đúng không ạ? Và những cái vật liệu mà chúng ta không dùng ở cái quá trình trước thì chúng ta cũng có thể reuse để save material and save cost. So if you could see on the right side, so when you, for example, using the laser in order to sinter material on the cross section, you see that on the edge. So the heat generated by the laser will influence the spot area and the surrounding one. And if the surrounding powders receive enough energies, so they can be sintered. Yeah, they can be sintered. And if the unfused powders, if people want to use the unfused powder and for the reusing process, and then those sintering powders need to be eliminated by the sieving techniques, for example. Thế thì nói một cách đơn giản cho các bạn hiểu như thế này. Khi chúng ta biết là chúng ta in 3D, chúng ta tạo vật liệu là layer by layer, phải không ạ? Giả sử chúng ta đang consider cái lớp vật liệu ở trên cùng như thế này, và cái tia laser của chúng ta như là một nguồn nhiệt đang cung cấp nhiệt để làm nung chảy cái loại vật liệu, các cái powders ở trên cái mặt cắt mà chúng ta cần phải thiêu kết ấy. Thì chúng ta biết là ở trong cái mặt cắt này thì đương nhiên chúng ta phải thiêu kết để nó đưa về trạng thái lỏng và dính kết lại với cái lớp vật liệu mà chúng ta đang thiêu kết và dính với cái lớp vật liệu trước đó, đúng không ạ? Tuy nhiên là kim loại chúng ta thì nó dẫn nhiệt, cái nhiệt nó có thể dẫn ra cái surrounding area, thì cái powders mà ở những cái vùng xung quanh, nếu mà nó vì một lý do nào đó nhận đủ nhiệt thì những cái vùng xung quanh này nó cũng là powders, nó cũng sintering, thậm chí là nó còn dính kết luôn cả lên trên bề mặt của cái chi tiết mà chúng ta đang thiêu kết. Đấy, để mà chúng ta sử dụng được, bởi vì những cái powders ở xung quanh này nếu như mà sau cái quá trình mà chúng ta tổng hợp vật liệu, chúng ta hoàn toàn có thể tái sử dụng lại, đúng không ạ? Tất nhiên là nguồn nhiệt này nó cũng làm ảnh hưởng ít nhiều đến cái cơ tính của surrounding powders rồi, nhưng mà nếu chúng ta quyết định sử dụng, đúng không ạ, thì chúng ta phải dùng cái biện pháp sàng lọc để loại bỏ những cái powders nó đã dính kết lại với nhau rồi, để đảm bảo là cái quá trình distribute cái vật liệu, cái spreading của cái vật liệu ở các cái chu kỳ sau nó sẽ được đảm bảo. Recycling methodologies, phương pháp để chúng ta tái chế. So as easier, people can mix unused powder with used powders. So one suggestion is to combine 1/3 unused powder, 1/3 overflow of feed powders, together with 1/3 build platform powders. Overflow powder is already modified with respect to the original. Seeing the temperatures is affected. Yeah. It is affected by the temperatures during the sintering or melting process. The part bed powders, the parting and sorting method. It's just for sorting by sieving, before mixing in order to eliminate some type of agglomerations or synthetic powders. Or to be used for the recycling process. Yes, so nothing special. Nothing special. So from the loading powders to the machines, and the powders can be used here. To be fed for the building process. And after the build, we have the powders recovered from the powders from the build tank, the recovered powder from the overflow, recovered from powder from Hooper. So all the collected powders must be sifted to, how can I say, eliminate the synthetic powders, or if possible, break up the agglomerates. If possible, So this means that after the sieving, we have the powder which are ready to be reused. And afterward, you need to mix, yeah, this powder with the new powders, 1/3 amount of new powders, and then we transport back to the machines and load into the machine and ready for the next build. Yeah. Okay. So I would like to start for the second chapter here. So do you have any question before we turn into the third chapter? So heat source for additive manufacturing. I let it here for a minute. Yeah, I know that you spend a time on writing your name. Yeah, then no question. Okay, so I will start with the third chapter. No, no, no. This is the aerospace material. Okay, additive manufacturing. Yeah, that third one. Okay. So this figure, okay. So the third chapter, we will talk about the basic function of heat source formator AM. So here we have the opportunity to discuss a little bit concerning the laser, the electron beam as a heat source. Yes, to use for heating the feedstock material, which can be either powders or wire. And of course, the heat source can be others, like the wire arcs additive manufacturing, like wire arcs, hồ quang. So for the powder bed fusion, can we use the laser or electron beam as the heat source in order to melt powders? Yes, to fabricate the electron beam assisted powder bed fusion. Both the laser and the electron beam can also be used by the direct energy deposition. And in addition to these heat sources, we can use the electric arcs to support the direct energy deposition process. And almost all of the direct energy deposition processes can use wire as feedstock material, and some can employ powders as the feedstock materials. And now I would like to talk a little bit about the molten pool. So the heat source intend to heat up the material to create a molten pool. Yeah. So the laser, for example, so the laser is focused on a small area, providing enough heat to locally melt the material on surface, and we have the melt pool here. So the direction of focus energies shocks on matters. Yeah. Will melt the matters if the energy is provided is enough. If the energy is provided is enough. Because why? Because when traveling from the mirror here, so the source, to the surface of the part, some energies is lost. Some, when reaching the surface, will be reflected, so will not absorb onto the material to heat up the materials. Others can be absorbed, but immediately radiated away in the form of heat. So some energy loss. No matter what is lost in terms of the loss before reaching the surface, or reflectly afterward radiate away in form of the heat. Yeah. So the portion which is remaining absorbed energies will play as will play a role as the for heating will play a role for heating the parts or heating the matters to create the molten pool at these positions. And you know that the heat source or the laser beam here travel along the path following the scanning vector actually. Scanning vector actually. And when it travels, it's followed by the molten pool. So when it's moved to the next positions, and the molten pool will be created, and therefore we call is will be followed by the molten pool when the heat source travels along the path. And basically, the fluid flow within the molten matter pool and the vaporization of the flow are generally difficult to control because it's occurs high temperatures. And the scanning to control the fluid flow within the molten matter pool and and the vaporized matter flow. Vì chúng ta biết rằng là khi mà chúng ta cần cái tia laser nó scanning lên trên cái cross section để tạo ra hoặc là để locally melt hoặc để melt cái lớp vật liệu ở trên cái bề mặt đó, đúng không ạ? Giả sử ở lớp thứ N đi, đúng không ạ? Chúng ta nó đang là ở dạng powder, chúng ta scan tia laser qua để tia laser nó làm nóng chảy vật liệu, đúng không ạ? Nó dính kết lại với nhau và dính với cái lớp phía trước. Vấn đề ở đây là tia laser của chúng ta đi nhanh quá, đúng không ạ? Nó dẫn tới là rất là khó để mà control được cái dòng chảy của kim loại lỏng ở trong cái bể kim loại lỏng nhỏ nhỏ này, và rất là khó để control cái dòng vật liệu nó đi và nó bốc hơi, bởi vì nếu mà lượng nhiệt nó lớn quá thì cái kim loại thậm chí nó bốc hơi ra luôn và chúng ta bị lost alloying elements, và đấy là có thể xảy ra. Nhưng mà nó là không expect, chúng ta không expect có cái hiện tượng vaporization, cho nên lượng nhiệt nó phải đủ nó compensate với cái lượng mà nó mất đi trong cái quá trình mà nó đi đến cái bề mặt kim loại, đủ để bù lại cái lượng nhiệt mà nó reflect ở trên cái bề mặt kim loại nó chưa absorb được, và đủ để bù luôn cái lượng nhiệt mà nó absorb vào nhưng mà nó lại radiate ngay lập tức away dưới dạng nhiệt. Thì cái tính toán để mà cái power của heat source này nó rất là quan trọng để nó cung cấp đủ lượng nhiệt để nó locally melt cái vật liệu ở trên lớp bề mặt khi mà chúng ta tiến hành quá trình additive manufacturing. Advantage in AM. So we know that if the oxygen is occur inside the building chamber, so the oxidation reaction can occur and we have the surface oxide layer. And once the molten pool flow, because we have the traveling of the heat source along the path, and the molten pool flow can break up the surface oxide layer and support the fusion and joining to the previous layers. However, 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 the disadvantages is uh, the vaporized matter can create the process disturbance. And since several low melting temperatures, several elements with low melting temperatures can be vaporized during this process, and we lost, and as a consequence, we lost our alloying elements, and the uh, composition of the material is changed, is modified, and it lead to the modification of property afterwards. So it is unexpected. Another advantages is the condensations. So sự ngưng tụ, condensation of vapor on the optical elements, yeah, will affect the, the working abilities of the optical elements, and therefore we need to clean or replace the optical elements because of that. And then we have considered, or we study the heat source for material in order to design better additive manufacturing parts. Yeah. And to be associated with the heat source to create the high quality parts. Laser. We know that laser, yes, is light. Yeah. And see, this is a light. This is a high energy density beam of photon. Light is photon. It's a wave, but it's also a photon. Laser can be transmitted and focused to small spot of energies. So when the energy is focused to a small area, and then it can be heat up, the material, especially metal, can be heat up to the melting temperatures, and we create the molten pool. Yes. The laser equipment, basically, we have beam power, uh, and the power can be up to 1,000 watt. The focus pulsar of fraction of millimeters. There are a wide range of laser technologies for additive manufacturing. So, for example, neodymium doped with yttrium aluminum garnet. This laser, just some group of laser technologies, just some introductions, so nothing more than that. Because we do focus on investigation of lasers, so that's enough. Direct diode laser, fiber laser, and the fiber lasers is among those with STEM. Since it has the high reliability, compact size, small size, and low maintenance cost. And on the right side of the slide, showing you the graphic description of the fiber laser principle. So basically, the laser diode transforms the electricity into photon. And then the photon or the light is then pumped into the fiber optic copper. Fiber optic copper. The copper have the core and the external part. The core has high refractive index. The cladding or the cover or the outside has low refractive index. So when the light travels through the cap, we have the internal reflection of the light in the core and travel through the fiber optic cover. So the reflection. So just inside the core of the cap. The fiber core is doped with the rare earth elements like yttrium. So the aim of doping is to interact with photon so that the electrons are excited into the higher energy level. So jump into the higher energy level like in the physics you study in the 12th grade. And when at the high energy level and when it jump down to the lower energy level, is release the energies in the form of photon, which produce more light. And that's why we dope the core with rare earth element to produce more light. This here. And then it's passed through the fiber black grating. It's actually the set of mirrors emit pulsing photons back and forth to reflect photons and pumped by diodes. And last is the collimating lens, which aligning the light to minimize spreading to create the focused laser beam. So output we have the focused laser beam to provide enough heat to the surface area which need to melt to create the melt point. Yeah, high energy beam. And on this line we consider the interaction between the laser and the materials. So different material will behave differently. So material can, in particular metals, we laser energy differently. So for example, aluminum or silver has the low absorption coefficient, so it's easier to be reflected. On the contrary, titanium has higher absorption of laser energy. So when the material in the form of liquid like molten metals, the molten metal will have greater absorption of laser energies comparing to the case of solid form. So if the metal is vaporized, so it will form some kind of cloud. Or the plasma is plasma, so the ionized gas. Yeah, the ionized gas. And both the vaporized matter and plasma can absorb the laser. So we lost the energies, the heat source, energy of the heat source, and prevent the laser from reaching points. So how can we melt the powders material from the powder bed? Yeah. So we need to compensate with the lost energy. The pressure created by the cloud of vaporized matter and superheated gas can create the depression in molten point. Here, pressure. And may create a defect like porosity or entrapped voice. So at high temperature, everything tend to expand. The cloud of vaporized matter is in the form of gas at high temperature, so it creates the pressure, and the pressure can have the effect on the molten pool and create some kind of porosity here. The ytterbium fiber laser normally has the operating wavelength of 1.07 microns. Yeah. Just some information regarding the fiber laser. Power up to 10 kilowatt, energy efficiency and free from maintenance up to 25,000 hours. So it's the reason that people use the fiber laser comparing to the other type of lasers. Yeah, electron beams is another type of heat source that can be used. As I remember, is the develop the technologies, for example, electron beam assisted particle fusion is used by NASA. Let's see what I'm saying. The productivity is somehow better than in the case of particle fusion using laser as heat source. But then the accuracies of the second case is better. Accuracy of the second case is better. That we have studied within the first chapter when we comparing about the laser or the electron beam, which can be used as heat source for particle fusion. So electron beam is the high energy density beam using electron instead of photons. So the figure on the right side show you the basic principle of electron beam gun, and the description is on the left side. We have the high voltage supply, and the cathode is heated to boil earth electron, actually to emit electron. Electron is then accelerated and focused by the grid cuff here, and go toward the anode and passing through the hole inside the working chamber. Inside the chamber here, inside the chamber here, the electron beam is focused by the electromagnetic coil and magnetic deflection coil to steer the beam, because you know that we have to scan through a certain area and then we need to align the beam to focus on the surface of the workpiece and to guarantee the scanning path. Yeah, following the scanning velocity, scanning vectors, scanning vector. The electron beam equipment, yeah, can be classified uh, as the based on the voltage. The beam voltage can be 60 up to 150 kilovolt. Yeah. The beam spot size fraction of millimeter is just how to the focus spot size here. And one specific thing is that the when you use the electron beam as a heat source inside the building chamber, you need to maintain the vacuum. The pressure of the vacuum should be smaller than 10 to minus 4 bar. And you need the high purity environment to prevent some kind of deflection of the beam, electron beam. and to minimize the contamination inside the building camera, of course. And for sure, everything has two side effects, and then the electron beam assisted material has a certain limitation associated with the life. Regarding cathode emitter, yes, regarding the maintenance and productivities of AM process. Because when you need to maintain and then you have to wait, and then to this extent, yeah, productivity can be affected. Industrial use of electron beam heat source can be used for welding the aerospace structures, nuclear application, and high production applications. Because I already mentioned that comparing to the case of laser assisted particle fusions, the use of electron beam as a heat source tend to enhance the productivities of the process, and therefore the industrial use of electron beam as heat source can be used for high production application. So we have two types of generator, low voltage and high voltage gun. Yes, I think that let's say, let me see. Yeah. I think that we can finish the slide, and we can continue the lectures next Thursday. So for the moment, I will select some the most important things to introduce to you, but not focus, not what I say, uh, discuss all of the content, but just focus on the most important things. Yeah. But let complete this slide, and then I will be here until 3:55, 35 for checking your attendance. And please remember that you should the start doing the assignment as soon as possible from now. Yeah. So when the course is finished, and then you have time to, how can I say, adjust and some uh, to do some modification if needed, and then you can submit the file or the hard copy to me for evaluation. Yeah. So don't don't forget. Advantages of using electron beam. Yes, we can couple the beam energy more efficiently to matter. Yeah. To disadvantages. Yeah, the energy beam need to be created and propagate within the vacuum. So to maintain the vacuums, you need the equipment. Yeah. So high cost equipment is needed. These disadvantages of using electron beam. The other thing is that electron beam can impinge on the metals, and during this process, it can create the X-ray. And X-ray is the detrimental to human health. And the other thing is that also belong to these advantages of using electron beam is uh, the energies provided by electron beam is high and typically has sufficient energy to vaporize the low melting point constituents, and is unexpectedly modifying the chemistry or composition of the materials and changing the properties of the material. And we do not want that. And not only the laser, but also the electron beam has the complex interaction with the materials. Yes. And since we have the complex interaction between the electron beam and the materials, and then the process is easy to be unstable. Yes, because we have the complex the process. Many issues need to be controlled, and if not, and then the process is unstable. Yeah, and that's the point. So the next class on the next Tuesday, I will focus on the last part of chapter 3. We will continue with the chapter 4. What we're focusing on a little bit on computers and so on. But we will have the fast review about the chapter 4 to have enough time to focus on the chapter 5 next week. Yeah, next week. And for the last 3 chapters, I think the 2 last days are somehow enough. Yes. And for those minor things that are not important, and I will let you read them at home. So don't worry. And now is the time for you to focus on the design. Yes. And do you have any questions regarding the chapter 2 and 2/3 of the chapter 3, or half of the chapter 3? No question. Yeah, no problem. Okay, so thank you for your attention, and I wish you have a nice day ahead. And see you next time. Yeah. So I'm still here. I'm still here until 3:30, 35, and check your attendance and answer the questions if you have.